So hello everyone, we are Runtime Brigade. Today we are presenting our graph-based robotic warehouse navigation and item similarity detection system. This project was built in Java using custom graph data structures, addressing a massive real-world challenge. So the problem statement. So the e-commerce and retail sectors in South Africa are expanding rapidly, creating a massive demand for smart logistics and warehouse automation. When an automated system processes an order, it faces two distinct challenges. First, extracting meaningful patterns from unstructured data, like identifying an item strictly from an image. Second, calculating the optimum physical route for an automated robot to retrieve that item on a busy warehouse floor. Our goal was to solve both problems under one unified mathematical framework. So the core concept for this project, so to bridge computer vision and physical navigation, we realized that both domains can be modeled using the exact same structure. A graph abstract data type. A graph consists of nodes connected by edges. In our solution, we built a custom generic graph abstract data type from scratch. Because it is generic, a node can represent two completely different things in our app. In the physical warehouse, a node is a one-by-one floor tile, and an edge is the traversable path to an adjacent tile. In our classification system, a node is a grocery image from the Freiberg groceries dataset, and an edge represents the visual similarity between two images. So let's look at how the classification side works.
Hi, I'm Candice, and I'll be taking over from my colleague. So the next part I'll be explaining is the classification via the KNN. Specifically, I'll be starting with the feature extraction and explaining how we went about it. So when a user uploads a query image, the computer can't simply see what that image is. So what we did is that we built an image feature extractor that scans every pixel and categorizes its red, green, and blue values into an array of 24 bins. We normalize this histogram by the total pixel count, giving us a mathematical DNA for the image. So what we did is that we dynamically built a temporary k nearest neighbor graph, drawing edges to the top k most similar images. So what we then did is that we used a majority voting. So if we set k to 5 and 3 of the closest matches are coffee, for example, then the system will confidently classify our query as coffee, even if the absolute closest single image was a false positive. So once the matching zone is identified, then it will trigger a second phase where the robot is actually going to go or navigate to that specific shelf.
So in this next portion of things, I will be showing you the interaction with our GUI. So the first thing I'm going to do is I'm going to load our grocery data set. Okay, so we're going to go ahead and we're going to do that. Okay. Okay, so now that our groceries data set, it is loaded, as we can see, I'm going to select a query image. So I'm selecting an image where, we want to go to, essentially. So let's go with juice. Okay, so I select the juice image, and there we go. And just like that, our robot identified the path, and it actually moved to our juice. Let's now find something else. We're going to go and we're going to find sugar. So choose a random sugar image, and just like that, it determined our path, and then it just moved to the item. I'm just going to do it one more time with a different item. Now we're getting water, and just like that, we are getting our water. And that's it from my end.
Now that the robot knows where to go, our warehouse is a grid-based graph. To find the best route, the user can select between two algorithms, Dijkstra's and A-star algorithm. A-star is highly efficient because it uses Manhattan distance to make a smart guess and pull the search towards itself. As you can see, we can select and then select our query image, which is just vinegar, and we can use A-star or Dijkstra, or then it makes a smart guess to figure out how to get to our vinegar using the fewer nodes than Dijkstra. But our warehouse isn't static, so we implemented a fully dynamic CRUD operation into our graph. As you can see, we can click on tiles to have new blockages, and we can left click on them to clear up these new blockages, as you can see. And now if we go back and we select vinegar again, new path to find vinegar, right? By right clicking, I simulate a congested aisle like a forklift in the way. This updates edge weight. To summarize, we successfully translated a complex problem domain into correct graph structures. We implemented a completely custom generic graph 80D to handle nodes, edges, and dynamic weights. We proved the system's logic and complexity by implementing custom image feature extraction without third-party APIs, a KNN graph for robust image classification, and both A-star and Dijkstra algorithms for optimal pathfinding. Finally, our JavaFX user interface not only looks clean, but actively facilitates the real-time creation, updating, and deletion of graph constraints, effectively simulating a real-world warehouse environment. Thank you for watching our presentation. We are Runtime Brigade.